Hello, welcome back. In today's video, we're going to be taking a look at the Northwest booklet, specifically the acid-based questions from that booklet. This is a highly requested section for me to cover, and so let's take a look at it. Question 1 says, two beakers A and B contain strong bases. Beaker A contains 500 cm cubed of barium hydroxide of unknown concentration X. Beaker B 400 cm cubed of potassium hydroxide of concentration 0.1 moles per dm cubed. Question 1.2 says calculate the number of moles of hydroxide ions in beaker B. So quickly, I'm going to just use the formula. N is equal to C times V. The concentration is 0.1. The volume is 0.4. Remember, 400 cm cubed is 0.4 dm cubed. We've got to do that conversion. And so we'll get 0.04 moles, but this is of KOH. So we got to look at the KOH and look at how it breaks. So you're going to get K plus and OH minus. Now, it's clear in this reaction that everything is in the ratio 1 to 1. So if this is 0.04, then this will be 0.04. And so that is our answer. Now, question 1.3. The contents of beakers A and B are added together in beaker C. The solution in beaker C has a pH of 13. Assume that the volumes are additive and that the temperature of the solutions is 25 degrees Celsius. 1.3.1, calculate the concentration X of the barium hydroxide in beaker A. And worth 8 marks. Now, 8-mark question usually tells me that it's going to involve quite a few calculations. Now, there's actually two ways of doing this. There's the conventional method and the unconventional method. So let's take a look at the unconventional method. And this is the approach that I took when I initially saw the question. So what I did was, I said, let's take a look and focus on the beaker B. So beaker B, I know the concentration. And so what I did was, I said, let's calculate the pH of the potassium hydroxide in that beaker. So we can do that quite easily. We'll say POH is equal to minus log of the concentration of OH minus. And we know the concentration of the OH minus. It's the concentration of the KOH. So minus log of 0.1. And that means that the POH is equal to 1. Now, since it's at 25 degrees Celsius, this whole thing is occurring at 25 degrees Celsius, we can use the KW formula, but this is again the unconventional method. So from here I can say that pH plus POH is equal to 14. That means pH is equal to 14 minus 1, which is 13. So from here, I thought about it. I said, okay, this has a pH of 13. And this has a pH of 13. So this must have a pH of 13. Otherwise, if we added them, then the pH of C won't be 13. Like, I thought that if you're adding B, and that has a pH of 13, and you're adding A, if it had anything other than a pH of 13, it's not going to give you a pH of 13 for C. So all of them should have a pH of 13. So then I focused on A. I said that A should have a pH of 13. Right? So that must mean that the concentration of A, or the concentration of the OH, let me rephrase that. The concentration of the OH minus in A should also be 0.1 moles per dm cubed, because that's going to give me a pH of 13 like we showed in this calculation. Now, if I know the concentration of the OH minus in A, and I'm saying that that is 0.1 moles per dm cubed, and I know the compound of A, that's barium hydroxide, I can work out the concentration. So BaOH2 will break, it'll give you Ba2 plus, and it'll give you 2OH minus. If this concentration is 0.1 and the ratio is 2 to 1, this concentration must be half of that. So 0.05 moles per dm cubed. And so that's the answer. It's a bit of an unconventional method, but I'll show you the other way as well. It is the more conventional method. It's the one that I think most examiners would be looking for when they are trying to mark it. So first thing, and this, let's call this option 2. So what I would do here if I wanted to do the longer method is I would say in beaker C, I know the pH. So I'll say that pH is equal to minus log the concentration of H3O plus. If the pH is 13, then minus log concentration H3O plus, then the concentration of H3O plus will equal 1 times 10 to the minus 13. Then I would go to my Kw formula. Kw is equal to concentration of H3O plus multiplied by the concentration of OH minus. Then if I want the concentration of OH minus, I'm going to do Kw, which is 1 times 10 to the negative 14, divided by concentration of H3O plus, we worked out as 1 times 10 to the minus 13, and that gives me 0.1 moles per dm cubed, which is the concentration of OH minus in the additive volume. So this volume here is 0.9 dm cubed. Why 0.9? Because this is 400 and that is 500. So 400 plus 500 is 900. 900 cm cubed is 0.9 dm cubed. Now, from here, I can work out the number of moles. So I'll say that the number of moles of OH minus is equal to the concentration, which is 0.1, times the volume, which is 0.9, and that is 0.09 moles of OH minus. Now this moles came from both beaker A and it came from beaker B. Now I can work out how much moles came from beaker B and then subtract it to get the moles in beaker A. So in beaker B, the number of moles, that's going to be equal to C times V. Concentration is 0.1, volume is 0.4. That means 0.04 moles came from beaker B. So that means in beaker A, you have 0.09 minus 0.04, and that is equal to 0.05 moles of OH minus in A. And remember now, in A, this was 500 cm cubed or 0.5 dm cubed. Now from here, we can calculate the concentration of the OH minus in A. And that's number of moles, which we worked out as 0.05, divided by the volume, which is 0.5, and that is 0.1 moles per dm cubed of OH minus in A. Then you go to the reaction, the BaOH2, and that breaks up into Ba2 plus and 2OH minus. And then from here, it should be familiar. If that's 0.1, this must be 0.05. Now this method There's a lot of extra steps, but the ending is about the same. So if you look at the unconventional method, it uses a lot of logic and we jump straight to the end. Whereas here, there's quite a bit of calculation just to get to the same point that tells you that the concentration of OH minus in A is 0.1. So again, sometimes for 8 marks, you can use a lot of calculation, but also there's often a more elegant solution. Now let's take a look at the next question. Next part of the question says, the solution in beaker C is titrated with ethanoic acid. It was found that 15 cm cubed of the solution neutralizes 30 cm cubed of the acid. The balanced equation for the reaction is. So 1.3.2 says, is ethanoic acid a weak or strong acid? Give a reason. So ethanoic acid is a weak acid. And why? It's because it ionizes partially. Okay. 1.3.3, calculate the concentration of the ethanoic acid. Now, to calculate the concentration, we can use the titration formula, where whenever there's complete or neutralization, CAVA over CBVB is equal to NA over NB. So we want the concentration of the ethanoic acid, so Ca will be unknown. The volume of the acid, they tell us, is 30. Now, when we use this formula, we don't even have to convert. Cb is the concentration of the base. Concentration of the base, we've been told, is 0.1. Then, we even worked it out. We worked it out as 0.1 also. Volume of the base, they tell me, is 15. That's equal to Na over Nb. You get from the reaction here 1 to 1. And now you solve for Ca. Ca is 0.05 moles per dm cubed. Let's move on. Question number 2. Sulfuric acid ionizes in 2 steps as follows. So H2SO4 plus H2O, and the reactions are there. 2.1.2, name or write down the name or formula of the substance that can act as an ampholyte in the above equations. Give a reason for the answer. So 2.1.2, so ampholyte is something that can act as an acid or a base. Here, it's going to be the HSO4 minus. That's because the HSO4 minus can receive a proton, becoming H2SO4, or it can give a proton, becoming SO4 2 minus. Question 2.1.3. The conductivity of solutions of HSO4 minus and H2SO4 are compared. Which solution will have a lower conductivity? So the one that's going to have a lower conductivity is going to be HSO4 minus. And why? It has to do with the Ka. So the Ka value is low. What does that mean? It means that it's going to ionize partially. It is a weak acid. And so fewer ions, meaning a lower or weaker conductivity. 2.2, the pH of a hydrochloric acid solution, HCl, is 1.02 at 25 degrees Celsius. Calculate the concentration of the HCl. Now, if you think of HCl, or look at HCl, HCl is monoprotic, meaning that the concentration of the H plus ions is going to be the same as the concentration of the HCl. So if I work out the concentration of the H plus, it's going to be the concentration of the HCl. So we use the pH formula. pH is equal to minus log concentration of H plus or H3O plus. pH is 1.02. That is minus log concentration H3O plus. Now the concentration of the H3O plus, which as we said is going to be the concentration of the HCl, is going to be 0.0 0.095 moles per dm cubed. Moving on, this HCl solution reacts with sodium carbonate according to the following balanced equation. 50 cm cubed of the HCl solution is added to 25 cm cubed of a 0.075 mole per dm cubed Na2CO3 solution. Calculate the concentration of the excess HCl in the new solution. Now, we can't use, for this question, CAVA over CBVB equals NA over NB. And that's because they didn't say anything about endpoint being reached. There's some HCl in excess. So we can't use this formula. We have to go a different route. And so the route we'll take is we'll start by calculating the number of moles of the base, which is the sodium carbonate. So that's going to be C times V. So 0.075 multiplied by the volume, and that is 0.025. Remember, now we have to convert to dm cubed. And that gives us 0.001875 moles of the base. Next, we can use a mole ratio to get the number of moles of the acid that reacted. So we'll say the mole ratio is 2:1. Therefore, the number of moles of the acid is going to be 2 times the number of moles of the base. So that's going to be 0.00375 moles of my HCl. And this is the amount that reacted. So remember, to get the amount that's in excess, you need to take the amount that you started with and you got to minus the amount that you used. So this is the amount that was used. So you use 0.00375. And we need to figure out how much we started with to figure out how much was in excess or how much is in excess. So to get the amount that we started with, the number of moles at the start, that's going to equal C times V. Now the concentration is 0.095. Remember, we worked this out early on. It's the same HCl. And that's multiplied by the volume. Now the volume is 0.05. Remember, 50 cm cubed. So we got to convert that. That's equal to 0.00475 moles at the start. So this is the amount at the start. So 0.00475 minus 0.00375, which gives us an excess of 0.001 moles. Now, we need to think about this container. So in here, we have 0.001 moles of HCl. Now, what's the volume? So the volume now is going to be the 50 plus the 25. It's going to be in 75 cm cubed, which is 0.075 dm cubed. So we can calculate the concentration. So the concentration of the HCl that's in excess is going to be 0.001 divided by 0.075, which is equal to 0.013 moles per dm cubed. Okay, let's take a look at question number 3. 2 groups of grade 12 learners were given separate experiments to conduct using a strong base and weak acids. So group 1, learners were asked to determine the percentage purity of a sample of oxalic acid. To do this, they followed the procedure below. They prepared a standard solution of sodium hydroxide by diluting 50 cm cubed of sodium hydroxide solution of concentration 0.63 moles per dm cubed to a volume of 1 dm cubed. Then they prepared the solution, they did some titration, and they given us the equation. 3.1.2 says calculate the concentration of the standard NaOH. So we are interested now in this. So there was a dilution that took place, so we'll use the dilution formula. So C1V1 is equal to C2V2. So the concentration at the start was 0.63, and that was in a volume of 50 cm cubed. We don't need to convert here. And that's equal to, okay, let's convert. It doesn't matter because they've given us the final in dm cubed. So 50 cm cubed is 0.05. And that's equal to C2, which is what we want, and V2 is 1. That means C2 is equal to 0.0315 moles per dm cubed. So that is now the concentration of the standard. 3.1.3 is for 7 marks. Calculate the percentage purity of the oxalic acid sample. 3.1.3, calculate percentage purity. Now, we need to understand what happened. So they prepared a solution of oxalic acid, they dissolved 0.25, and they did a titration. Okay, did it reach? Yeah, it neutralized all, so we can use the formula CAVA over CBVB is equal to NA over NB. Now the concentration of the acid, do we know the concentration of the acid? No, we do not. So Ca, the volume of the acid that was neutralized was 75 cm cubed. So that's 0.075 dm cubed divided by concentration of the base, we worked it out, 0.0315. The volume of the base was 40.02, which is 0.0402 dm cubed. And according to the reaction, the ratio NaNB is going to be 1 over 2. So now we can calculate the concentration of the acid. Concentration of the acid is then 0.008442 moles per dm cubed. Now that we have the concentration of the acid, we can calculate the mass of the acid that's actually in here. So remember the equation C is equal to M over capital M times V. We can rearrange this. We'll get that the mass is equal to concentration times molar mass times volume. Concentration is 0.008442. The molar mass of oxalic acid is 90. And the volume that this is in, now remember the oxalic acid, they told us that it was 75 cm cubed. So that's 0.075. Now that will give us a mass of 0.0569 grams. So this is the amount of oxalic acid that was pure in that impure sample. So we can calculate percentage purity now. The percentage purity is going to equal to how much was pure. This amount was pure, 0.0569 divided by how much was impure, 0.25 times 100, and that gives you 22.79%. Let's look at group 2. So group 2 said, or they were tasked, learners were required to find the concentration and percentage of ethanoic acid in household vinegar. To do this, they used the following procedure. Diluted vinegar sample by placing 25 cm cubed household vinegar in 250 cm cubed volumetric flask. They titrated the diluted vinegar with a solution of NaOH to concentration 0.2. Calculate the pH of the NaOH. Okay, so again, just like earlier, NaOH will give you Na plus OH minus. So if you calculate the concentration of the OH minus, that's going to be the concentration of the NaOH because it's the same. Now, pH, what we can do first is we'll say POH. Let's calculate POH. That's equal to minus log the concentration of OH minus. Now we said before that the concentration of the NaOH will be the same as the concentration of the OH minus because it's 1 to 1. So minus log 0.2, and that is equal to 0.69897. Now from here we can say that pH is equal to 14 minus pOH, which is this, and that's equal to 13.30. Next part, in the titration, 15 cm cubed of the diluted vinegar sample needed 30.25 cm cubed of the sodium hydroxide solution for the endpoint to be reached. 3.2.3, calculate the concentration of diluted vinegar solution in ethanoic acid. So it reached endpoint, so we can do CAVA over CBVB is equal to NA over NB. So they want the vinegar, which is the acid, so we don't know what that is. So Ca, the volume of the acid was 15 cm cubed, so 0,015. You don't have to convert, but just do it. Cb, concentration of the base, 0.2. They told us it was 0.2. And the volume of the base was 30.25. So 0,03025. And that's equal to Na over Nb, which is 1 over 1. That means Ca is equal to 0.40 moles per dm cubed. And the next part, 3.2.4. If 1 cm cubed of vinegar has a mass of 1 gram, calculate the percentage ethanoic acid by mass present in the vinegar. So again, there's a few ways to do it. I'll do a bit of an unconventional approach here. So the way I'm thinking here is I'm saying that if 1 cm cubed is equal to 1 gram, then in our sample, so our sample, remember, is 15 cm cubed. That's the amount that was titrated or neutralized. You're going to get 15 grams of vinegar. Right? Now, in this 15 grams, you have some ethanoic acid. We don't know how much it is. Okay? And so what I want to do here is I want to calculate how much we actually have. So the mass is equal to concentration times molar mass times the volume. So we worked out the concentration. The concentration was 0.4. The molar mass of, in this case, it is acetic ethanoic acid. So ethanoic acid is 60 times the volume. We know the volume is 15, so 0,015. And that gives us a mass of 0.36. So we have 0.36 in 15. So 0.36 grams in 15, or out of 15, times 100, and that is 2.4%. However, it's important to note the question is asking for how much was in the vinegar, the original vinegar. This vinegar that we're talking about is a diluted amount. So we need to undo this dilution. So remember at the start, they tell us that there was 25 cm cubed. It was then diluted to 250 cm cubed. And then from here, they took out 15 cm cubed. So if this is 2.4%, they poured out. So concentration is still going to be the same. This is going to be 2.4%. Now, we have to undo this dilution. So this amount here will be more concentrated because they diluted it. So if you're working backward, it's going to be more concentrated. So how much did they dilute it by? So they diluted it by a factor of 10, because from 25 to 250 is multiplied by 10. So we must multiply by 10 here. So we'll get 24%. And that's our answer. Again, it's a bit of an unconventional method. There are other methods, but that's the method that immediately I thought of. So 3.3, sodium ethanoate undergoes hydrolysis. 3.3.2, how will the pH of the water be affected by the hydrolysis reaction? So to answer this question, analyze the salt. So the salt is CH3, COO minus, and Na plus. So this came from CH3, COOH. This is a weak acid. So this will be a strong conjugate base. Na came from NaOH, which is a strong base, which means that this will be a weak conjugate acid. Now, the one that's going to undergo hydrolysis, the ion that's going to undergo hydrolysis, is the one that's going to be strong. So this is going to undergo hydrolysis. So CH3, COO minus, is going to react with water. And since it's a strong conjugate base, bases accept protons, so a hydrogen is going to go there. You're going to get CH3, COOH plus OH minus. The presence of the OH minus means that the pH is going to be greater than 7. They want to know, will the pH increase, decrease, or remain the same? The pH will increase. Now, question 4. Question 4 says the conductivity of 3 acid solutions A, B, and C is investigated. Same temperature. The brightness of the bulb in the apparatus shown below is used as a measure of the conductivity of the solutions. The brightness of the bulb, so I'm reading here, the brightness of the bulb for each of the following, or each of the solutions is compared. In which solution A or B will the bulb be brighter? Give a reason by referring to the type of acid. So if I'm comparing A and B, I'm going to say that it's going to be A that's going to be brighter, because both of them are strong acids, but H2SO4 is diprotic, meaning that 1 mole, so it's going to ionize completely. So 1 mole of H2SO4 is going to give me more than 1 mole of H+. So more ions. Whereas HNO3, it's going to ionize completely, but 1 mole of HNO3 will give me 1 mole of H+. So if I'm comparing the ions, I'm getting more ions from H2SO4, so the conductivity will be better. 4.1.2, or 4.1.3 rather, in which solution B or C will the bulb be brighter? So in this case, I'm going to go with B, and the reason is because HNO3 is a strong acid, whereas CH3COOH is a weak acid. And because CH3COOH is a weak acid, it's going to ionize partially, meaning from 1 mole of the acid, I'm going to get less than 1 mole of H+. Okay, question 4.2. A hydrochloric acid solution, HCl, is standardized by titrating it against 25 cm cubed of a 0.04 mole per dm cubed sodium carbonate solution. At the endpoint, it is the balanced equation for the reaction is. Okay, weird, but okay. 4.2.1, calculate the concentration of the HCl. So it reached endpoint, so we can use our formula CAVA over CBVB is equal to Na over Nb. Now, they want to know the concentration of my acid, so Ca is unknown. The volume of the acid is 19.5 divided by concentration of the base. They've given us as 0.04. The volume of the base that was used was 25. And Na over Nb, there's 2 to 1. So the concentration of my acid is going to be 0.103 moles per dm cubed. Okay, 4.2.2. Suppose a few drops of water are present in the burette before it was filled with HCl. How will the volume of HCl be needed, or needed to reach the endpoint be affected? So because it's important that they mentioned it was present before it was filled. So what that's going to do is it's going to, the H2O is going to dilute the acid. And so you're going to need more acid to neutralize. So the answer there is it's going to be greater. Now let's look at this part. A concentrated household product chemclean contains ammonia as the main cleaning agent. To determine the amount of ammonia present in 1 dm cubed of chemclean, the following procedure is followed. 20 cm cubed of chemclean is added to a 250 cm cube flask. The flask is then filled to a 250 cm cube marked with distilled water. The diluted solution is titrated against hydrochloric acid as calculated in question 4.2.1. During the titration, 22 cm cubed of the diluted chemclean solution is neutralized by 18.7 cm cubed of the HCl solution. The balanced equation for the reaction is: calculate the mass of ammonia in 1 dm cubed of chemclean. So here, again, it reached endpoint. There was a titration and it was neutralized. So I'm going to use the formula again. CAVA over CBVB is equal to NA over NB. Now, we know the concentration of the acid. We worked it out in the previous question. So that's 0,103. How much of acid did they use? 18.7 divided by CB. And the volume of the acid was 20. The volume of the base was 22. And the ratio here is 1 to 1. Therefore, the concentration of the base is going to be 0,0875 moles per dm cubed. Now, a few things happened here, and so we can't use this concentration to calculate the mass. So let's figure out what happened. So you had the one dm cubed container. And from here, you poured out 20 cm cubed. So you poured. And from there, you diluted to 250 cm cubed. Right? So you diluted it here. And from here, you used 22 cm cubed, but you poured it here. Now, whenever you are pouring, let's use a different color. When you are pouring, the concentration remains the same. So here and here, the concentration is the same. But when you are diluting, the number of moles is the same. So we're going to have to undo some things here. So if the concentration here is 0,0875, then the concentration here is going to be 0,0875. Now to go from here to here, we have to undo the dilution. So we'll use the dilution formula. C1V1 is equal to C2V2. We know the concentration, 0,0875. We know the volume is 250. And that's equal to we want the concentration here, so it's going to be C1, and the volume is 20. That means C1 is equal to 1,09 moles per dm cubed. So the concentration here is going to be 1,09. And then since from here to here it was poured, it means that the concentration here in the 1 dm cubed will also be 1.09. So now that we have the concentration in the original chemclean, we can work out the mass. So we can say mass is equal to concentration times molar mass times volume. Concentration is 1.09. The molar mass of chemclean, which is ammonia, is 1417 plus or times the volume, which is 1. And that gives you 18.53 grams. Now the last question, Will the pH of the solution at the end of the titration be greater than 7, equal to 7, or less than 7? So what we do is we look at our salt. So you have NH4 and Cl minus. Now the NH4 came from NH3 and the Cl minus came from HCl. So HCl is a strong acid, so this will be a weak conjugate base. It's not going to undergo any reaction. NH3 is a weak base, so this is going to be a strong conjugate acid. This will undergo hydrolysis. So NH4 plus H2O. Since this is an acid, it's going to donate a proton there. You're going to get NH3 and H3O plus. The presence of the H3O plus tells us that the pH is going to be less than 7, and that means that, yeah, the pH should be less than 7. Let's take a look at question 5. To identify metal M in an unknown metal carbonate, the following procedure is carried out. Step 1, 0.198 grams of impure MCO3 is reacted with 25 cm cubed of 0.4 moles per dm cubed nitric acid. Step 2, that's carried out as well. Assume that the volumes are additive. The following reaction takes place. So 5.2.1, calculate the number of moles of barium hydroxide that reacted with the excess HNO3. So 5.2.1, what we'll do here is we'll just use N is equal to CV. So the concentration is 0.15, the volume is 0.02. That gives me 3 times 10 to the minus 3 moles of barium hydroxide that reacted with the excess HNO3. 5.2.2, calculate the pH of the solution after step 1. So 5.2.2. So if I know the number of moles of barium hydroxide that reacted here, I can work out the number of moles of HNO3 that reacted there. So I can say that the number of moles of the acid is going to equal 2 times the number of moles of the base because of the ratio. So 2 times 3 times 10 to the minus 3, that's 6 times 10 to the minus 3 moles of my acid. Now remember, this is what was left over after the first reaction. So we can say that the excess after the first reaction is 6 times 10 to the minus 3. So now that we know the number of moles in excess, we can calculate the concentration. So the concentration of the acid that's in excess is going to be 6 times 10 to the minus 3 divided by the volume. So after step 1, the volume is only 25 cm cubed. So 0.025, and that's equal to 0.24 moles per dm cubed. Now, if they want the pH, we need the concentration of the H3O plus. Now, if you look at HNO3, HNO3 is a strong acid and it's monoprotic, which means that the concentration of the HNO3 is going to be the concentration of the H3O plus. So pH is going to equal minus log of the 0.24, which gives me a pH of 0.62. Question 5.3. Calculate the percentage purity of the MCO3 in the sample. The percentage purity of the MCO3 in the sample is 85%. Identify metal M. So here, what we'll do is we will say that 85% of the impure is pure. So 85% of the 0.198, that's equal to 0.1683 grams, and that's the pure amount. Now, to calculate what M is, we use the formula N is equal to mass over molar mass. So what we want is the molar mass. We know the mass, but we don't know the number of moles. So we need to work out the number of moles by going through these reactions. So reaction 2 and reaction 1. So we'll start with reaction 2 and then we'll make our way forward. So what we can do is we'll start by, let's look at, I think, Yeah, it'll be easier if we just look at the number of moles of the acid at the start. So how much acid did I have at the start? So at the start, I had 0.4 times 0,025. So that's 0,01 moles. So this is the amount that I had at the start. The number of moles that I used in the second reaction is equal to 6 times 10 to the minus 3. Yeah, we calculated it here. That means in reaction 1, the acid that was used was 0,01 minus 6 times 10 to the minus 3, which is equal to 4 times 10 to the minus 3 moles of acid in reaction 1. Now, if I look at the mole ratio, the acid to the carbonate is 2 to 1. So the number of moles of my carbonate, which is the base, is going to be half the 4 times 10 to the minus 3. So that's 2 times 10 to the minus 3. So this is the number of moles. So if I know the number of moles and I know the mass, I can calculate the molar mass. So the molar mass is going to be the mass, which is 0.1683, divided by the number of moles, which is 2 times 10 to the minus 3. That is equal to 84,15 grams per mole. So now we know the total molar mass, we can calculate what M is. So M plus the molar mass of carbon is 12, plus 3 oxygens, so 3 times 16, is equal to 84.15. So M is equal to 24.15. Then we check on the periodic table, that is equal to, so M is magnesium. Okay, let's move on. Question number 5 again, but this is a different question. Two acids X, Y, and HY, HX and HY rather, of equal concentrations are compared. The pH of HX is 2.7, the pH of HY is 0.7. 5.1.2, which acid is stronger? Give a reason for your answer. It's simple. HY is stronger. It has a lower pH. 5.1.3. HX ionizes in water. The Ka value is 1.8 times 10 to the minus 5. Is the concentration of the hydronium ions higher than, lower than, or equal to the concentration of HX? So it's going to be lower than, and the reason is the Ka is low, which means that the acid ionizes partially. (5.2) Learners add 150 cm cubed of sodium hydroxide of unknown concentration to 200 cm cubed of a 0.03 moles per dm cubed HCl solution, as illustrated below. They find that the pH of the final solution is 2. Assume that the volumes are additive. They've given us the reaction, and they say calculate the concentration of the H3O plus ions in the final solution. So I'll do pH is equal to minus log the concentration of H3O plus. So 2 is equal to minus log concentration of H3O plus. The concentration of H3O plus is then equal to 0.01 moles per dm cubed. Now question 5.2.2. Calculate the initial concentration of the NaOH. Okay, so the first thing I'm going to do here is I'm going to make some deductions here. So the pH is 2, which means that, so the pH is less than 7, which means that HCl, which is the acid, must have been in excess. Must be in excess. Right? So from here, I can look at the dissociation of HCl. So HCl will give me H plus and Cl minus. This, I have the concentration. So 0.01. And since HCl is monoprotic, this concentration will also be 0.01 moles per dm cubed. Now that I know the concentration, I can calculate the number of moles of the HCl that's in excess. So the concentration is 0.01. The volume, they tell me that the volumes are additive. So this total volume here is 0.2 plus 0.15, which is 0.35 is the volume. So I can calculate number of moles of the acid that's in excess. That is 0.01 times 0.35. And that is equal to 3.5 times 10 to the minus 3 moles of HCl in excess. So in here, I have 3 times 10, well, 3.5 times 10 to the minus 3 moles of HCl. Now I can work out, well, they give me some information here. I can work out the total amount of HCl that I had at the start. So the number of moles of HCl initially is equal to the concentration, which is 0.03, times the volume, which is 0.2. And that is equal to 6 times 10 to the minus 3. Now that I know how much was left over, I know how much I had at the start, I can work out how much was used in the reaction. So the number of moles of the acid that was used in the reaction is 6 times 10 to the minus 3 minus 3.5 times 10 to the minus 3, which is 2.5 times 10 to the minus 3 moles. Now that I know the number of moles that was used, I can do a mole ratio to calculate the number of moles of the base. Since the ratio is 1 to 1, the number of moles of NaOH is also going to be 2.5 times 10 to the minus 3 moles. Now that I know the number of moles and I know the volume of the NaOH, I can calculate the concentration. So the concentration of the base is going to be 2.5 times 10 to the minus 3 divided by the volume 0.15, which is 0.02 moles per dm cubed.